Hello, I'm Jae-hoon Jung, a PhD student in Seoul National University. Today, I would like to talk about SnuRHAC. This work is part of my PhD thesis and advised by Professor Jae-jin Lee. Also, it is a joint work with Moray Incorporation. Heterogeneous systems accelerated by GPUs are widely used, and many programming models have been proposed. Early GPU applications focused on fully exploiting a single GPU. However, data size is getting bigger and computation is getting more complex. As a result, we need to use multiple GPUs. A program designed to use a single GPU needs to be rewritten for multiple GPUs. The problem is that it is not as simple as it seems. The programmers need to fully understand the characteristics of applications and how to use a programming model to orchestrate multiple GPUs. The problem gets worse if they use multiple GPUs in a cluster. To solve the problem, we propose SnuRHAC. SnuRHAC stands for a runtime for heterogeneous accelerator clusters developed in Seoul National University. SnuRHAC provides an illusion of a single GPU for the multiple GPUs in a cluster. It is based on CUDA. When a programmer writes a CUDA program for a single GPU and runs it under SnuRHAC, SnuRHAC automatically distributes workload to GPUs in a cluster and manages data across the nodes. It also exploits two prefetching techniques to maximize performance. All things are transparent to users and no source code modification is required. Before going into the details of SnuRHAC, I will briefly explain CUDA Unified Memory. Unified memory is a component of the CUDA programming model. It provides a memory space that can be accessed by both the CPUs and the GPUs in a single address space. Pages in the space are automatically migrated on demand. Let's look at the behaviors of with an example. Suppose we have allocated a space. There exists a host space at the CPU side and the GPU spaces at the GPU side. Suppose that the CPU has accessed page 1 and page 2. Both pages reside in the space at the CPU side. Now, GPU 0 accesses page 1 and GPU 1 accesses page 2. As both pages reside on the CPU, each GPU raises a page fault. Then the NVIDIA driver catches the interrupt signals and migrates the faulted pages. Finally, the GPUs replay the faulted memory accesses. While significantly reduces the burden of a programmer, it does not guarantee good performance. As many pages are migrated on demand due to page faults, it causes a lot of overhead. To reduce the overhead, the programmer needs to add CUDA prefetch commands or user hints. Let's look at the overview of the whole component. SnuRHAC targets a cluster where each node is equipped with multiple NVIDIA GPUs. Also, each node is connected with a network that supports remote direct memory access, which is called RDMA. The operating system kernel has the NVIDIA driver and the SnuRHAC driver. The NVIDIA driver allows CUDA runtime to control GPUs. It also handles various interrupt signals from GPUs, including page fault interrupt signals. The SnuRHAC driver extends to the cluster by hooking the NVIDIA driver's page fault handler. It is installed in every node and communicates with each other through RDMA. In the user space, the CUDA runtime and the SnuRHAC runtime run. In node 0, the host node, a CUDA program runs on top of the SnuRHAC runtime. SnuRHAC runtime provides wrapper functions of CUDA API functions, and the CUDA program calls these wrapper functions. When the CUDA program calls a wrapper function in the host node, the SnuRHAC runtime in the host node sends appropriate commands to the other nodes. Here, I will explain some notable wrapper functions of SnuRHAC. When the host program requests device memory allocation, the SnuRHAC runtime in every node allocates a space. With the SnuRHAC driver, multiple GPUs in the cluster see the same address space and share data through When the host program requests host-to-device memory copy, the SnuRHAC runtime in the host node copies data to the host space at the host node. When GPUs execute the kernel, the cluster migrates the required pages. When the host program requests device-to-host memory copy, the SnuRHAC runtime in the host node copies data to the host space at the host node. When the pages do not reside on the host space, the cluster migrates them. Finally, when the host program requests CUDA kernel launch, the SnuRHAC runtime in the host node partitions the workload and sends kernel launch commands to all nodes. To utilize multiple GPUs in a cluster, there are two important things to consider: how to distribute workload and how to manage data across the nodes. First, I will explain how SnuRHAC distributes the workload. To distribute workload to GPUs, we need to partition the CUDA grid that is specified in kernel launch command and make each GPU execute the partitioned grid. The right diagram shows how SnuRHAC partitions the grid. It assumes that the computing power of GPUs is all the same. The algorithm prioritizes partitioning in Z dimension first, then Y dimension, and then X dimension. Most of the CUDA program is designed to coalesce global memory access in the X dimension of the thread block because of the thread ID calculation rule in CUDA. Moreover, adjacent blocks have a high possibility to access the same page. Thus, it is desirable to have contiguous thread blocks in X dimension in a partitioned chunk of blocks. After partitioning the grid, we need to make each GPU execute the partitioned grid, not the original grid. To do this, SnuRHAC generates a new kernel based on the original kernel code. It extracts original kernel code from the application binary file and modifies it. Here is an example of modified kernel code. We offer the code at the source level for easy understanding. Changes from the original code are highlighted in green. In lines 2 to 4, the kernel receives additional arguments to know which thread blocks are assigned to the GPU that executes the kernel. In lines 6 to 9, the kernel filters out the thread blocks that are not assigned to the executing GPU. The newly created kernels are compiled at runtime and executed when the CUDA program launches the kernels. Now, I will explain how SnuRHAC manages data across the nodes. Cluster is an extended version of CUDA. With SnuRHAC driver, multiple GPUs in the cluster see the same address space and share data through cluster For cluster the SnuRHAC driver needs to keep track of the location and status of all pages in the space. To track information of pages, we need a data structure to store the information. In NVIDIA driver, it manages the pages in the space by grouping them into multiple blocks. Maximum 512 contiguous pages are grouped into a block. Each block object contains all information of pages in the block. However, the SnuRHAC driver needs to record the information of pages across the nodes. Therefore, it manages an additional data structure called block descriptor for each block. A block descriptor has pages location and protection status across the nodes for the corresponding block. One issue here is that when we store a block descriptor in a single node, it can cause severe network contention. To reduce the contention, we distribute every 32 block descriptors in a round-robin manner to each node. Let's see how the SnuRHAC driver handles page faults with an example. Suppose that a page fault occurred in GPU 1 in node 1. The page fault handler in the SnuRHAC driver fetches the fault buffer in GPU 1. Fault buffer is hardware in NVIDIA GPU which stores the information for faulted accesses. The handler sorts faulted accesses by page addresses and groups them by blocks. For each faulted block, the handler finds a node that owns the corresponding block descriptor. We call this node BD owner node. Then it sends a block lock request to BD owner node. The BD owner node sends a response to the faulted node if no other node has locked the block. When node 1 receives the response, it sends the list of faulted accesses obtained from the step 1 to the BD owner node. The BD owner node looks up the list and finds the nodes where the faulted pages are resident. We call these nodes page owner nodes. Then it sends the IDs of the discovered node to faulted node. Also, it updates the block descriptor based on the information from the faulted access list. After node 1 receives the list of nodes that have faulted pages, it requests pages to the page owner nodes. The page owner nodes copy the faulted pages to their main memory and pin them, and send pinned addresses to the faulted node. Node 1 reads the faulted pages through RDMA, then copies and maps the pages to the space of the faulted GPU. Finally, the faulted node sends a block unlock request to the BD owner node and sends a replay signal to the faulted GPU. As mentioned earlier, on-demand paging causes a lot of overhead. We exploit several prefetching techniques for the performance. To prefetch pages when a kernel executes, SnuRHAC needs to know the kernel's memory access patterns. Our static prefetching technique is based on MAPA. MAPA relies on both a source-level compiler analysis technique and runtime information. It extracts memory access patterns of a kernel in symbolic expressions and classifies the access patterns into 10 categories. SnuRHAC exploits memory access patterns that fall in the affine and constant categories from MAPA. If possible, MAPA outputs every memory access expression in the affine function of block index variables, thread index variables, and induction variables. The example shows an output of MAPA for a vector addition kernel. The first line shows the name of a buffer and the second line shows the access type. The third line shows the access pattern category. Finally, the memory access expression is expressed. This figure shows how SnuRHAC's static prefetching works. When a CUDA program launches a kernel, the SnuRHAC runtime in the host node loads memory access patterns from MAPA. Then it partitions the workload and distributes the workload with the loaded access patterns. The SnuRHAC runtime in each node calculates each thread block's memory access ranges using information from MAPA. Then it enqueues prefetch commands to appropriate prefetch queues. The SnuRHAC runtime maintains a prefetch queue for each GPU. Also, a CPU thread called prefetch scheduler in the SnuRHAC runtime dequeues the prefetch commands and issues them to the SnuRHAC driver. While the SnuRHAC driver in a node prefetches the requested pages, the SnuRHAC runtime in the same node executes the partitioned kernel. It is impossible to analyze all different types of memory access patterns statically. To complement static prefetching, SnuRHAC uses two dynamic prefetching techniques. Adjacent page prefetching is similar to adjacent cache line prefetching. When all memory operations for a memory object are read-only within a CUDA kernel, the SnuRHAC driver prefetches all pages in the faulted pages block. When adjacent page prefetching cannot be used, SnuRHAC driver uses correlation prefetching. Correlation prefetching is also one method of cache line prefetching. It uses past sequences of references or miss addresses to predict and prefetch future misses. Records of cache miss addresses that are correlated are stored in the correlation table. In SnuRHAC, we use this technique to the page level. The SnuRHAC driver manages the correlation table for each GPU and keeps track of faulted pages. The figure shows how correlation prefetching works. Each row of the correlation table stores faulted page address and num levels of successors. In each level, the num_suc entries are MRU ordered from left to right. It also keeps num levels pointers to the table. These pointers point to the entries for the address of the last fault, the second last fault, and so on. The table shows a snapshot when page fault has occurred in C. Now, a page fault occurred in A again. The algorithm updates the entries for B and C and updates the pointers. Also, it prefetches all the entries in the row of A. In CUDA a page cannot be mapped to multiple processors due to memory consistency problem. This can cause frequent page faults between processors due to page sharing. However, if all memory operations for a memory object are read-only within a CUDA kernel, the user can set read-only flag through user hint API. Then the NVIDIA driver duplicates the page to multiple processors. Thanks to MAPA, the SnuRHAC sets this read-only flag automatically without user hint. Some applications are not suitable for multiple GPUs. One example is that uses atomic operations in CUDA kernels. The SnuRHAC inspects kernel code if there is an atomic operation. Another example is an application that has many pages shared between GPUs. When write sharing occurs frequently, it can cause significant performance degradation. To avoid this, SnuRHAC calculates the access range of write operations from each GPU. Then, it calculates the amount of overlapping in the access ranges. If the ratio of the overlapping amount to the total amount of access ranges exceeds a predefined threshold, SnuRHAC executes the kernel using only a single GPU. For evaluation, we use an 8-nodes cluster. Each node has 4 Tesla V100 GPUs and InfiniBand EDR network card. We use 18 applications from various sources. These are the schemes we used in evaluation. CUDA means using the original CUDA runtime only. SnuRHAC shows the performance without any prefetching. SnuRHAC SP shows the performance with the static prefetching only. SnuRHAC SPDP shows the performance using both techniques. First, let's look at the single GPU performance. This shows the speedup of each application over the original CUDA runtime on a single GPU. SnuRHAC is much slower than the original CUDA runtime on average because pages are migrated on demand. SnuRHAC SP and SPDP are, on average, faster than the original CUDA runtime. Especially for these two applications, SnuRHAC SP and SPDP are much faster than the original CUDA runtime. These applications require relatively big device memory size and spend most of their execution time on memory copying. Thus, prefetching is quite effective. The multi-threaded copying mechanism in the SnuRHAC boosts their performance too. This figure shows the speedup of each application by varying the number of GPUs. The speedup is obtained over a single GPU which runs each application using the CUDA runtime only. SnuRHAC shows the poorest performance because pages are migrated on demand. SnuRHAC SP shows similar performance to SPDP but shows the notable differences for TPAC and LavaMD. This is because MAPA cannot analyze most of the memory operations in the kernels. Thus, static prefetching does not work well. SnuRHAC SPDP shows the best performance for all applications. The figure below shows the ratio of the kernel execution time to memory copy time measured on a single GPU using the CUDA runtime only. The scalability of the applications is significantly affected by the characteristics of the applications. In general, applications that have high ratio of the kernel execution time scale well. These three applications have very high ratio of memory copy time. They show poor scalability because they spend most of the execution time on copying data. MRIQ and particle filter launches multiple kernels. Each kernel has different memory access patterns to the same memory object. It causes frequent data movement between GPUs on every kernel launch and degrades the performance. We compared the performance of SnuRHAC with multi-GPU applications in CUDA code samples. The figure shows the speedup obtained by varying the number of GPUs. The result indicates that SnuRHAC achieves almost the same scalability and performance as the handwritten multi-GPU applications. To conclude, SnuRHAC extends CUDA unified memory for a cluster. It automatically distributes workload, manages data across the nodes, and exploits static and dynamic page prefetching techniques to improve performance. These are all transparent to users and no source code modification is required. While we implement SnuRHAC based on CUDA, we can apply the same techniques to other programming models and hardware that support page fault mechanisms. Finally, the source code of SnuRHAC is publicly available on our website.